Hi, in this work, we are exploring compiler support for near data computing, and this is a joint work between Penn State, University of Pittsburgh, and Tubitak Bilgem. And the paper makes two main contributions. First, we explore in detail the potential of near data computing when the near data computing opportunities are restricted to certain hardware components. And secondly, we explore compiler support for near data computing. In particular, we present two compiler algorithms. Exploring the architectural support for near data computing is not the main focus of this work. What I would like to say in this slide that we explore near data computing, or we assume that the hardware supports gives supports for near data computing in four hardware locations. One of them is link buffer, the other one is cache bank, the third one is memory controller, and fourth one is the memory itself. And we explore two different metrics to quantify the potential of near data computing. And one of them is arrival window. Basically, arrival window captures the difference between the arrival times of two operands, let's say A and B, that are involved in near data computing at a particular location. It's one of the four locations that I mentioned in the previous slide. So, for example, let's say we are going to do, let's say A plus B. A arrived at that particular location, let's say that the cache controller, and then B arrived. The difference in cycles between them gives us the arrival window. Basically, this gives the amount of time that A needs to wait for B so that we can perform near data computation. Now, clearly, we want this time actually to be small. We want this time to be small so that we don't want actually B to wait too long for A. Now, these plots here give the results, give the detailed results, and for different benchmarks on the x-axis, and y-axis is given the distribution of the arrival windows for different hardware components. Now we can see from these results that arrival window lengths vary significantly depending on the benchmark, depending on the application program that we are running, as well as the specific location under consideration. For example, in Swim, 14.3% of the arrival windows at cache controller are less than or equal to 20 cycles, whereas for the same benchmark, when you focus on the memory controller, it is the arrival windows that are less than or equal to 20 cycles constitute only 7.7%. So since the arrival window puts an upper bound for the waiting time, different applications are expected to achieve different amounts of benefits from near data computing. And to capture this benefit, actually, we use another metric called the break-even point. Break-even point gives the time that leads a better result compared to conventional execution. For example, let's say that the operand A arrived at a particular location, and then how long is it going to wait? So break-even time point is the right amount of time actually for A to wait. Okay, and if the arrival window size is bigger than the break-even point, it means that the near data computing probably is not going to generate a better result than the original conventional execution. So we want the break-even point smaller than the arrival window so that we can catch it using some strategy. We can catch or we can figure out the right amount of time to wait. And this plot here is showing or comparing the arrival window distribution to the break-even point distribution. And we see that in general, break-even points are lower than the arrival windows, which means there is an opportunity to take advantage of near data computing. Now, this plot here, the first one on the upper right, is actually showing the performance benefits that are achieved over the conventional execution when using different strategies. So, what are these strategies that we are? What are the strategies that we are using? So the first one is a straightforward near data computing. Basically, the first operand comes to a particular point that you want to perform near data computing and waits for the second one. And when the second one comes, you perform the computation there. And if the second one doesn't come at all, then you actually revert back to conventional computation. Whereas wait 5, 10, 25, and 50 correspond to actually a certain to cases where actually we wait a certain fraction of the over arrival window. So in the, for example, wait 10%, operand A comes, and if the arrival window, this is a simulation-based study, and if the arrival window is, let's say, 100 cycles, then we wait actually only for 10 cycles for the second operand to come. If in 10 cycles the second operand doesn't come, so we go back to conventional computation. Whereas the last wait is a strategy actually that is a strategy that looks at actually the previous waiting time, and if it's beneficial, then the conventional computing, if that wait time then uses that. And what is shown actually in this plot, to summarize, is that if you just do straightforward near data computing, you are not going to get much benefit. On the other hand, if you use something like actually an Oracle scheme that somehow magically decides whether to perform near data computing or not, and optimally decides actually how much to wait, and if necessary trades off near data computing opportunity with data locality optimization, then we see that actually there might be significant benefits. And whereas if you look at actually this other schemes, wait 5%, 10%, or last wait, we don't see much benefit from these strategies either, just like the straightforward near data computing. And whereas Oracle actually shows significant saving. The reason that the last wait doesn't perform very well, because we showed it actually in the paper that there is not much regularity actually in optimal wait times. The last graph here, the last plot, is showing actually the distribution of the near data computing opportunities that Oracle exploits. So Oracle, as you can see here, exploits the near data computing opportunity in each of our 4 potential locations. And now actually these results overall indicate that neither implementing a fixed waiting time when the A comes, it is going to wait for B, neither implementing a fixed waiting time nor employing a prediction-based waiting strategy generates better results than the original case. So the question is that, but on the other hand, we see that Oracle scheme helps. So there is a potential. The question is whether the compiler can help. Now we implemented 2 compiler algorithms and tested them. And here in this slide, I give an overview of them, how where they fit actually in the entire compilation process. So we take the input code and parallelize it if it's not already parallel to begin with, and then apply some conventional locality optimizations in the second stage. And then we employ a cache misestimation. And the reason actually that we have this component, because we need to know where actually to perform near data computation. For example, in order to perform it in the L2, then we need to know that actually we need to have an idea whether we are going to miss in L1 or not. And similarly, in order to perform it in memory controller, then we need to know that actually whether it's going to miss in L2 or not. So we need a cache miss estimation strategy, and then we feed our code and as well as the description of the architecture to the cache miss estimator. And our algorithms also take the architectural description, and they also take the input from the cache miss estimator and generate the output code. And then we perform some low-level optimizations, such as CMD optimizations and so on, and generate the output code. Now, the important point here is that these two algorithms differ from one another in that the first one performs only NDC. In other words, it does not consider data locality. Whenever it gets an opportunity to perform a near data computation in a particular hardware component, it does that, it takes advantage of that. Whereas the second one is more selective in performing near data computation. It trades off near data computation opportunity with data locality optimization. And first, let me talk about our cache miss estimation. We use actually a previously proposed strategy called cache miss equations. We use an enhanced version of it that has been proposed previously from Princeton. And for the benchmarks that we used, we achieved in L1 81% accuracy in hit miss estimation, whereas in L2 nearly 73%. So considering that actually this is a prediction at the compilation time, so we believe that these values, this accuracy, these prediction accuracies are reasonable. Now let me explain actually what the first algorithm 1 is trying to do. So suppose that in this simple program we got 3 statements. We got other statements as well, but I'm just focusing on this 3, and that this one accesses X, this one accesses Y, and then there's a computation that we are performing later, X plus Y. Now the goal here is that in X plus Y, I want to take advantage of near data computing. So I want to perform I want to compute X plus Y in where actually where the data is. So to do that, we enhance ISA using an instruction called precompute. And it is like a conventional compute instruction, except that it performs a specified computation in one of our 4 target locations that I mentioned earlier. And compiler inserts a precompute interaction wherever, depending on where we want to exploit near data computation. So let me give you specific scenarios. So for example here, let's say that this is S1, S2, S3 from the previous slide. Now what I do actually here, the goal here that in algorithm 1 is to bring the access to X, access to Y, and this computation close together. So the idea is that I'm going to move here Y from this point to this point, and I'm going to move X plus Y from this point to this point, so that when I have, let's say, I want to perform X plus Y in the, let's say, cache, so I got more confidence that X and Y are going to be in the cache, okay? And on the other end, if I predict that X and Y actually are going to be cache misses, then I'm going to insert X plus Y here, but this time I'm going to take advantage of the near data computing opportunity in the network on chip. So in this particular case, I'm moving Y and X plus Y together. Now in the second case, I'm keeping the access to Y in this place and move X and X plus Y. And in the third case, I'm moving all 3 of them. This is the most general case, but I want to emphasize that in all these movements, or all these movements are performed in a dependency aware fashion. In other words, we move, the compiler moves the data access and computation if and only if it doesn't break it doesn't violate any data dependency. Now, in the case of NOC, we actually take an additional flexibility or additional knob, you can call it, which is the routing flexibility. So what we do, for example, if you look at actually this two accesses in a network on a chip-based many core, they intersect only here. So this is the only place actually that you can, let's say, you can actually perform near data computing. But on the other hand, if you change the routing a bit, again, it is kind of a minimum distance routing, and if you change the routing, now you actually maximize the overlaps between these two paths or signatures, as we call it, and then you increase the chances or increase the number of hardware components where you can perform near data computation. Now, so far, I described it without paying attention to the data locality optimization. Sometimes, although there is an opportunity to take advantage of near data computing, you may not want to do that. And this is showing an example on the right-hand side. And the issue here is that if I want, just like in the previous slides, I can bring S1, S2, and S3 together, let's say somewhere at the beginning, and so that I can perform X plus Y near data. However, doing so actually may not be very beneficial in this case, because Y has later reuses. In fact, Y has a lot of reuse here. So instead of maybe actually performing near data computation, let's say in L2 cache, I might actually just bring Y to L1, as in the conventional execution, right? And take advantage of data locality. So algorithm 2 compared to algorithm 1 performs this trade-off. So it's more selective in exercising near data computing. So in such cases, for example, it actually takes advantage of locality. Our implementation actually is parameterizable or parameterized. It's tunable in the sense that you can consider different degrees of reuse here. For example, here Y is used 2 times after this target computation. Maybe actually for this case, it is still okay to perform X plus Y in a near data computing fashion. But in some other cases, it might be a different story. So this how many reuses that you trade off actually to take advantage of near data computing, that is something that you can actually tune in our implementation. Now I would like to present some experimental results for both algorithm 1 and algorithm 2, and this is showing the behavior of algorithm 1. So in other words, for each benchmark, it shows the distribution of the components, distribution of the cases where we exploit near data computing. For example, we can see actually that in, let's say, this B waves, for different components in cache, in network, in memory controller, in main memory, we take advantage of near data computing. And when you compare different benchmarks behave differently. For example, in this particular benchmark, Imagic, here there's not much opportunity in main memory, whereas in, let's say, this FFT, there are many more opportunities to take advantage of near data computing in main memory. Overall, we see that most opportunities actually are in the network, and the reason for that, in on-chip network-based many-core architectures, both L2 accesses and the main memory accesses exercise the on-chip network, and we also have this routing flexibility, and these two factors combined make actually on-chip network a good target for near data computing. And this the plot on the bottom right, on the other hand, is showing the case actually. It's showing the last bar in this graph for each benchmark, showing the performance improvements over the conventional execution. So we see significant improvements on an average, actually 22.5% improvement algorithm 1 brings over the over the conventional execution without exercising near data computing. The remaining bars show what if we apply near data computing on only one component. If you consider near data computing, let's say, only in cache, that is what the first bar shows, or only in on-chip network, that is what the second bar shows. And the main actual observation from this graph is that for the best results, that is really critical. It's really important to exploit near data computing opportunities in all our four target locations. Now, this is showing the behavior of, these plots are showing the behavior of algorithm 2. And algorithm 2 brings on average more than 25% improvement. It is higher than algorithm 1. And the main reason for that, it has actually a better cache behavior. It has higher cache hits in both L1 and L2 levels. And the reason actually that it has that, because it does not indiscriminately uses, it does not blindly use near data computing in every opportunity. Whenever there is a significant reuse of one of the operands that are involved in the near data computation, it actually does not, at the time, it doesn't exercise near data computing. Instead, it allows the data actually to come to the higher levels of the cache hierarchy. And it has a better, it's a lower miss rate than algorithm 1, and consequently has better overall savings. So in this talk, I try to give an overview of our algorithms and try to give a very high-level view of our experimental results. In the paper, there is more detail of our implementation, and there's a more detailed evaluation of our workloads, and including sensitivity analysis on the different parameters of our algorithm, as well as the target architecture. Thank you.